So right here we have a scene that's shot from a drone in a city, and here's the estimated optical flow. Now to estimate this optical flow, we're using a deep neural network called RAFT to do this. And we'll go through this code in a bit. I also have other tutorials that go through RAFT and how to set it up. But the point of this is that if we want to detect motion when the camera is moving, an optical flow, even a deep optical flow, is not going to be viable for a computer vision system unless we're able to denoise this background motion. So the reason why the estimated flow is red right here is because the camera is actually moving horizontally from frame 1 to frame 2. It's very subtle. You can't see it with the bare eye, or you might be able to, but it's very hard to. But the flow detects this, and this noise actually wipes out the flow estimation. Now, if we look at the magnitude of this flow, we can still see some. We have a mover here, 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 even here, and we can actually use the angle to get some. And this angle right here is kind of washed out for this whole left side right here. But even though we can see this manually, it's actually very hard to threshold this and send it further down a computer vision pipeline. So let's see what I mean by this. So if we take the histogram of the flow and the magnitude of the flow, we can see that we have this whole thing right here. It's all spread out around 6. So we might deduce that the average motion of the camera is about 6, and then all the actual object movers are here and maybe even here. But so we can try to threshold this and get a mask to detect the movers, and we see we don't do very well. We're doing it by the mean. Let's see what the mean is. The mean is going to be roughly 6. So let's do something smaller, maybe 5, and bam, we're washing the whole mask out. We're letting way too much noise in. So one thing that we could do is we could try to account for the motion in a naive way. So the naive way is to actually estimate the speed from the motion. So we're taking the mean across axis. So the flow is a two-channel matrix. Right. So we have the shape of our flow right here, and then each of these channels, one is the horizontal flow, and the U and the V flow is the vertical. So we can see that we move at about positive 6.3 and a 0.55 vertically. So we can actually correct the magnitude by subtracting the speed in each direction to the flow, and then we can re-threshold again. And you see we can actually get much better results, but this isn't cutting it. We still have this giant mask right here, and you can see that when we actually go into the magnitude of this corrected histogram, that it's still noisy. We still have some outliers here, which is good, but we have this whole chunk of noise. We have outliers that are hidden inside of this noise. And in this tutorial, we're going to find out how to get these out, and it's going to be using a RANSAC algorithm. So the top of this tutorial, I have an outline of some of the things that we're going to do. So the first thing we're going to do is we're going to estimate the optical flow, which is what we've already done. And for this, we're going to depend on a deep flow estimation, because a classic flow estimation like Fahrenbach or Brock's optical flow, they're unable to estimate the movement of these smooth areas. So we have the smooth street right here, and the camera motion, even though it's a smooth area, needs to have a corresponding flow displacement because the camera has moved. Now, a deep method is able to estimate this, but an old classical method is going to have an almost zero flow right here, just a very low level of noise in these areas where it's smooth. But in the case of RAFT, it's a deep neural network. It's able to estimate pretty accurately the flow for all pixels. So once we estimate the flow, we want to find out what the background optical flow is. So in here, you can see that, all this stuff right here, the street, the lights, the trees, the fence right here, this is background. And then these cars right here, these cars that are moving, we can actually see in some of these cars and pedestrians, the bicyclist, we can see that they're moving. That is the foreground. So we model this entire flow as a combination of the foreground and the background flow. And the final thing is we are going to obtain a mask by thresholding the foreground. So essentially the foreground is going to be a denoised version of the optical flow that we're interested in, and once we get the denoised version of that flow, we can perform a simple outlier detection and detect the moving objects. So this approach is going to heavily rely on a RANSAC algorithm that's going to help us model the background optical flow. So the main idea is we want to solve for this H matrix to model the background flow. And so I'm going to write something right here, which I kind of forgot to, but we have our background flow. Maybe I did put it in here, but yeah, right here. So here's the notation right here. So here's the model of the optical flow with the comprised of the background and the foreground flow, our H matrix that models our background flow. And at this side, we have the 2D pixel locations, the X and the Y, and then we have the projected pixel locations where we project the X with the horizontal flow and the Y with the vertical flow to get the projected pixel locations from frame 1 to frame 2. This leverages the optical flow vectors, and now we have the quadratic expression of the pixel locations. So we're actually going to model the background flow as follows. We are going to model the background flow FB is XH minus P. So we have this X, this quadratic right here of the pixel locations, times our model, and this is going to get us our apparent flow at the new locations, and we actually subtract out the original pixel locations, and we're going to be left with the flow. So what's going on here is we're actually in this RANSAC algorithm right here, we're actually solving for the flow using this linear least squares, this expression right here. So before we go through this algorithm, something we're doing right here, I'll just do a little LaTeX. We have our projected flow Y minus our estimated flow, and then squared. So we want to minimize this right here. So this is really okay, it came out right. So this is really a minimization problem, and we minimize this with linear least squares, and you could look this up on Wikipedia for the derivation. You essentially take the first derivative and solve for 0. It's a basic calculus, and you get this expression right here. So there's a little bit of LaTeX. I'm going to leave out the subscripts because we're just doing a very high-level overview of this. So, and Y. Oh, looks like I forgot the $sign. So if you didn't know, you could actually do some LaTeX in a Jupyter notebook if you wrap it in $signs. So this is what we're doing right here. We're solving for this H matrix. And just a quick outline of this algorithm. We're going to subsample the projected pixels. So this is a RANSAC algorithm, and we're going to just take random samples on each iteration. And we're going to take a subsample of pixels, P, and get their projected flows, or get their flows F, and add them together to project the flows from frame 1 to frame 2. And we do this for a subsample, and the next step is we can take our known X matrix that we also subsample using the projected P's, and we compute the sample model. Then we compute the background right here, and then we can see if the error between the background and the actual computed flow is low enough below a certain threshold. If it is, we consider it an inlier. So if we get enough inliers, we can actually compute our model using only the inlier points, and then we compute the inlier background flow, and then we take the MSE again. If this is the lowest MSE in all our iterations, then we save the model, and then we save the error right here. So that's the overview. I actually have an article that covers this in a lot more detail and kind of tells you why all this stuff is happening. I'll link it below if you would rather read through that. And this tutorial, or this video, we're mostly going to attack the code and kind of visualize things as we go along. So that being said, let's dive in. Let's get started. But before that, let's take a look at the results. So here are the results on a video scene where we have the camera panning. And you can see for the most part, even though we seem to struggle just a little bit during these pannings, we're able to track all these objects, especially the large ones, and we can even track some of the small ones here in the background. But I do have a minimum threshold that's actually going to prevent us from detecting the smallest ones. And also, we're limited by the ability of RAFT to detect the flow of objects that are pretty small, which is not exactly too good at. So here's another one right here. This is going to be close to the test scene that we're actually doing, and we could see we're getting a pretty good track on these things. And even though we're unable to break some things out, for the most part, we're actually getting a lot of individual objects here. So this is pretty good. So let's see how we can actually do that. So the first thing we have are library imports. I am using motion detection utils.py. I have several other videos that go over what's going on in here. We're actually not going to use any of these except for these things right here, draw bounding boxes and create GIF from images. I have other videos that go over it, or you can look on GitHub and see for yourself. Write a comment if you don't understand anything. I'd be more than happy to explain in more detail. But the code we will be going over is this constrained ransac.py. So we will go over this when we get to it, but that's going to be the majority of this video. So we're going to import the model. I've already forked this, the RAFT model. I've put it in a folder that I have called Mars Challenge. You can put it anywhere, but I am basically adding this, loading the model, and loading my data path from the Visdrone dataset. I'll include the link in the bio. If you want to know more about this, I already have videos that I will also link for how to get started with RAFT. So we're going to use a situation where we have a lot of horizontal motion and in these two frames. I'm going to go ahead and compute the optical flow using an inference function right here that comes with the RAFT implementation. We're going to separate the flow. We're going to convert the flow to NumPy, and then we're going to convert this NumPy flow into its magnitude and angle so we can actually get a pretty good visualization. So here's our initial visualization right here from frame 1 to frame 2. As we saw earlier, it's very hard to distinguish. We might get a little bit better if we go ahead and compute the magnitude and angle, and we can see we actually can break this stuff out, but as we saw previously, we are not able to get a good estimate on it. So let's just kind of gloss over what we've already seen. We see that this distribution of the flow is around a number n. In reality, we expect this distribution, we want this distribution to be close to 0 because we know that most of these objects right here are stationary. This whole road right here should not be moving. And this fence right here, all this stuff here shouldn't be moving. We should have a very small distribution of non-zero flow. And that's what we're going to try to get. We're going to see how to extract the foreground and how to obtain the detections from that. We'll see that the foreground actually does have a distribution that is very, very, very close to 0 besides a few outliers. So here's what we did earlier. We tried the threshold and mask, did not have much luck. We tried here earlier, we tried to remove the speed from the flow estimation, did quite a bit of an improvement right here, but we still have this awful thing right here, this ring around the edges, and we can't seem to estimate the majority of the flow. So we can see this distribution is a little bit better. We're not quite centered around 0 like we want to be, but we have some more detections that are here that are hidden in the noise, and we're going to find out how to extract those using RANSAC. So right here is the lines of code that we need to obtain the H matrix, and the first one we have right here is getPX. We take the shape of the flow and we put it into this function. So let's go and see how to use this function. So the P and PX stands for the points. So I will just go ahead and show this right here. So we have P. So this is a 2D matrix of all the possible points in our flow image. And the X is actually the quadratic sample of the points in the flow. So let's see how I grabbed these right here. So the first thing that we did is we get a mesh grid of the height and width. So the mesh grid does is it gives us indexing values for a grid of the shape that we pass into it. So we've passed in a shape for the x value, we've passed in 0 to w, and we have our wh. So we have 0 to w, and then we have 0 to h right here for the y value, and it kind of helps to plot these. So if you're not sure what mesh grid does, we have low to high values along the columns, and then we have low to high values along the rows. So we start at 0, and then we go all the way to the max value of y, and we can see we go to 535 for y. Along the rows and x, we go from 0 to 951 along the columns. So this basically gives us all the possible indexes in our image, the size of our flow. So what we want to do is we want to reshape these into vectors, and then the next thing we want to do is we basically just stack these two vectors together to get p, and then the next thing we do to get x, we simply just express our polynomial as in terms of position. So we have all the x positions squared, all the y positions squared, x times y, x, y, and then we add the 1s right here, and that gives us our x. So that's all we're doing with that. In the next function, we have the sampling index. So the sampling index does is this gets our sample index, which is going to be our divvied up image, or divvied up image pieces that we're going to have based on these two, which I'll explain in a second. The total number of possible samples and the number of actual samples here. So let's dive in and see what's going on. So I will copy this down here. Let's see here. All right. So we're doing another mesh grid. Let's see where. So x index right here. You see it's a massive thing. We're going along the rows, and we have these divvied up right here. So we're basically taking squares along of our original image of a shape, 9 fit, what is it, 9? I already forgot. We're taking squares along our original image. That's 536 by 952. And what we're doing right here is the next thing we're doing is we're just going to compute the total number of points to sample based on the shapes that we're passing to it. And this is going to be not directly dependent on width and height. It is dependent on these variables right here. So let's go ahead and copy this just for reference. So the S is the edge length to break the image into squares, and that's what we are doing right here. Is we are doing a lid space, and we're just gonna plot this right here. Can't we plot? It's not what I wanted to do. So this is what we are doing. We're gonna make this an int because we're not too concerned with the size of these squares. We can have them approximate. We'll see why. So we're basically going to chop this image up into different sections. And I will grab this right here. We're going to do a mesh grid over these to get every second. So what this mesh grid is doing, it's obtaining two squares. We have squares from 0 to 31 and 0 to 33 and so forth. And then we're going to get the total number of squares and then the total number that we can sample. So we're going to say P is the portion of squares to sample. So we basically chop this image up into squares and we sample only a certain portion of it. In this case, we're only sampling from half the squares. And once we do that, we're just going to reshape these possible indexes into a column vector. So this is x index. So that's just one giant column vector. We could actually do them. We could actually just get the index. We just stack them together right here with index. So bam, here's our possible samples right here. Now I have a visual right here. I'm going to just kill that. I am going to show you what we're sampling from. Maybe this will make it a lot better. So right here, we take our index, and this code right here, this is a random sample. So we are doing pseudo random sampling in general. So this index defines where we're going to sample from. This index right here essentially lets us so this index right here, this is going to be the center of every square. So by having this index right here, we are able to guarantee that we are going to have even coverage, or relatively even coverage, of the entire image. And doing so, we actually just take a random chunk of these samples. We're like, okay, I'm going to just sample, X to Y. I'm not going to sample everything. I'm only going to sample a portion out of this. So that's what we're doing here. And then when I sample a portion out of it, I'm like, okay, I'm just getting these pieces right here. I'm not getting everything. We don't need to get everything in order to obtain a decent sample to estimate the background flow. So that's what's going on here. And this right here, the CRA, here is the constrained. We call this constrained RANSAC. So let's see what's going on with constrained RANSAC. So one thing we're doing right here, we're going to use numba. We're using a loop. General, it's not gonna. A loop's never efficient in Python, but we can make it a little bit better by using numba's JIT decorator. I noticed a slight improvement from here, but all you gotta do is import numba from numba, import JIT, and then set no Python equal to true. And if you have a loop in numpy 9 times out of 10, you're gonna get a pretty good speed up. So let's go ahead and get started. So first, we're going to declare the best error, and we're going to set our H matrix to zeros. Next, we're going to have our flow, our numpy flow that we pass in right here. We're just going to reshape it to a column vector. And then we're going to initialize some matrices to speed things up, to make sure things run smoothly. We're going to have our m×2 column matrix of image indices that we're going to sample from. And what this is going to do is that this will actually hold the number of samples by 2. And then right here we have our polynomial that we're going to store right here. And this S denotes sample. So we're actually only storing the number of samples that we have. And you can see right here we have a pretty small amount. We're not using a good bit, 263 samples out of our whole image. And then the number of possible samples, we have height times width is 510,000. So we're using a very small chunk. Yeah, about, I forget the order of operations. So less than 0.1% is what we're using. And we'll see that this is actually sufficient for us to get a good background flow. The reason for that is because we're taking multiple samples. So right here we initialize the background flow. The background flow is always going to be like just the same size as the original flow. So let's get started. Once we go into our iterations, we obtain the sample points using our randomly sampling from our sample index as shown here. We can store these in 2 vectors, xs and ys. And here we are able to obtain the UV flow samples, and then we are able to project the UV flow samples, or project the original points using the UV flow samples from frame 1 to frame 2. And now we can construct the polynomial that we're interested in helping our model. So right here we're able to use the linear least squares solution to fit the data to our model. So we are fitting this, trying to multiply this linear polynomial by our projected samples to see if we can get an H matrix that's able to project this linear polynomial to the actual background flow. So that's what we do right here. We project this polynomial to our background flow using the linear polynomial, and then we subtract out the original points and we are left with the background flow. So now we're going to get the inliers. We're going to take the mean squared error of the background flow and the original flow, and if we have this lower than some threshold, we consider it an inlier. So an inlier in this case is going to be the background, and an outlier is going to be our foreground, in other words, a moving object. So if we have a large enough amount of inliers detected, we are going to recompute the H model and recompute the background flow using only the inliers. And this will hopefully give us a better fit. So we do this again, we get our X polynomial and we get our projected points. We refit our data to the inliers, and then we get a new background model, and we compute the mean squared error again. And then we see if our mean squared error is better than our best error, and if it is, we save it and we save the model. And then we return the model H and our best error. So that is it right here. We can see, we're going to run this again, and I just print the shape. We can actually, let's just display H. So right here you can see our H matrix. We actually have some pretty small values, and then here is the best error that we obtained, 317. And remember, that is the sum across all inlier pixels, which is, given that we have 500,000 pixels, 317 is not a very high error. So once again, here is our sampling methodology that we are using. We are just taking random points on random divvied up areas on the image. And here's the step where we can actually use our best H model to get the predicted background flow. So this being said, here's kind of the moment we've all been waiting for. We are going to use the original flow. We're going to take our background flow, subtract it from the original flow to get the foreground flow. Then we're going to convert these to magnitude and angle, and we're going to see what they look like. So I have a plot of everything right here, but we could look at them individually. Here's the original flow right here. Let's look at this one right here. So here's the original flow, and here's the background flow. So you can see right away on this angle side on the right, we are immediately able to model this very high angle value right here, or whatever this is. I'm not actually sure why this is such a strong difference from here to here, but it is. But what's more interesting, we're able to get a pretty accurate background flow estimate. We're able to determine, the model is able to determine that these edges have a high flow. And so when we subtract them out right here, we can see that we actually have a fairly denoised image. And even though it looks similar to some of the stuff we saw earlier, we're going to find out in a computer vision system we could actually do an outlier detection on this foreground flow and easily detect the movers. And this angle right here, this thing just went haywire. I'm not really sure what happened, but we're not using the angle anyway. We're only using the magnitude. So we could separate the horizontal and vertical flow. We can see we have some pretty good separation. It's a little bit blurry, but this is an artifact from RAFT. And now, let's see, we have the background and foreground flow, but I have another one of all three of them. So right here we have the original flow magnitude. We still have this middle at around 6, and then the background flow magnitude is what's interesting. The range we cover goes from about 4.5 to 8.5, and here in the original flow we go from about 3.5 to 9.5. So we definitely clipped out some of the outliers by separating the background flow from the foreground flow. But what I like even more is this foreground flow. We can see in this foreground flow almost all the values are very close to 0. Now in reality the values are going to be not exactly 0 but close because of image noise, camera vibrations, and just errors in estimating the foreground flow. So this foreground flow goes from 0, and we have outliers starting at about 0.5 all the way up to 7. So these outliers right here are our movers. And now we're going to perform a simple outlier detection to obtain these movers. So what we're going to do here to get our threshold, we're going to have our hyperparameter, or sensitivity parameter, right here. Let's call it sensitivity hyperparameter, since we can change it to adjust the sensitivity of our detection threshold. And we're going to take the mean plus a scaled standard deviation, scaled by our sensitivity, and we're going to use that to get our motion mask. So this is it right here. We basically take our foreground, we take any evaluate pixel above our threshold and determine it to be a detection, and anything less is not a detection. And you can see we basically have all the movers right here, and besides these clusters full of multiple movers that we saw earlier. So scroll back up to that real quick. Yeah, right here. So we have all these things chunked under the same thing. We weren't able to break it out. And that's actually from the RAFT algorithm. We could maybe chop this image up and run RAFT individually and try to get some better resolution, but we're not going to go down that path this time. So let's see how to get the bounding boxes from this motion mask. And we could actually heavily leverage OpenCV for this. So a couple things to note when we get these bounding boxes. We're going to actually... What we're going to do is we're going to detect the contours, and then in each contour, we're basically going to use CV to bounding rect on the contour object and get the bounding box. A couple of things we're going to note. We're going to filter out minimum bounding box area and maximum bounding box area. Maximum bounding box area isn't really useful in this case. Sometimes it is, but I find that RAFT is pretty good. It isn't going to detect any massive things that aren't true detections, but we do want to filter any super noisy, like whatever this is right here is probably not a real detection. We want to get rid of that. And another thing, even though we're able to accurately model the background here, that's not always the case. Sometimes we get erroneous detections on the edges. This thing right here is a real detection, but sometimes we do get some stuff around the corners that are not real. And for that reason, I want to get rid of bounding boxes that have a center, or contours that have a center that are too close to the edge. So I set that edge threshold to 50. I find that might be a little too high for this data set. Maybe 25 would be better. So that being said, we could actually put this in a pipeline. So here's the basic pipeline. So we compute the deep optical flow, convert it to NumPy, all in the same line. We get the shape of the flow. We get the P and the X, the points and the polynomial expansion of X. And now we get the index, the total number of samples, and the number of samples. And then we obtain the H matrix right here. CRA fast right here is the same thing. The only thing I did was try to just reduce some matrix initialization to speed things up. It didn't really make a difference, so I'm not even going to bother to use it. So right here is where we compute the background flow, and now we extract the foreground flow right here, and then we obtain the magnitude, and right here is where we obtain our motion mask. And as an optional thing, we can clean the motion mask using morphology operations. I'm not going to do that for the sake of speed. This thing's pretty slow in Python since we're using a giant loop. In reality, this thing would probably be written in C++ under the hood. A lot of stuff in OpenCV is written in C++, even though they go through loops like this. So they're pretty fast. And then right here, we run our initial detections function on our detections, and we could return them, or if we want to perform non-max suppression, we can do that, and I have other videos that show how to do that. So right here, we're going to just run a quick test on our pipeline. So what we're doing right here is we're actually going to resize the frame to half. These frames are actually too big to run on my computer with RAFT. It crashes due to memory. We see it takes about a full second, and that full second comes from this constrained RANSAC algorithm, since we're running a pretty massive loop through Python. So maybe we can optimize that with Python or something else. And right here are the results. So we're able to distinguish most of the larger movers, and then these things are here that are clustered together, these smaller ones. These smaller objects in the distance tend to actually get clustered together. So that's all for this one. Right here, we can run it on a video clip. We can show more detections right here, and we can even save it as a video and even make a GIF. So I'll let you look through the code. I encourage you to download the code and play around with it and see if you can follow along and understand it. So that's all for this one. I'll see you on the next one.